Hello everyone, welcome to week 14 of our subject. Today, we'll explore the propulsive characteristics of a steam power plant, focusing on how steam turbine components work together to convert thermal energy into mechanical power for propulsion. Our main learning objective for this lesson is to explain how a steam power plant produces propulsive power and how its performance is affected by operating conditions like pressure, temperature, efficiency, and more. A steam power plant operates on the Rankine cycle, which involves four main stages. So as you can see in our diagram of the Rankine cycle, we have the boiler, turbine, condenser, and pump. So first, pressurizing the water using a pump. Second, heating it in a boiler to produce steam. Third, expanding steam in a turbine to produce work. And lastly, condensing the steam back to water. So in propulsion systems, the turbine mechanical work directly drives a propeller or generator shaft. So let us discuss the steam turbine components. So we have different parts. So first is the stationary parts. So we have casing, a robust cylinder that contains the high pressure, high temperature steam and the internal components. Next is nozzles and diaphragms. Nozzles are fixed components that accelerate and direct the steam flow onto the rotating blades. Diaphragms can partition the casing into pressure stages and hold the nozzles. Next is steam chest. Houses the control valves such as the governor valve and overspeed trap valve. Next are the rotating parts. First is the rotor, the rotating assembly of the turbine, which includes the shaft, wheels, and blades. Second, blades, or buckets/vanes. Attached to the rotor wheels, these blades are acted upon by the steam, causing the rotor to spin and convert steam's kinetic energy into rotational energy. Next is the shaft, the central shaft of the rotor, which extends outside the casing and connects to the driven equipment like a generator. Lastly are the support and control systems. First is the bearings. Support the heavy rotor and maintain its position, often using journal bearings. Next is the seals. Various types of seals such as labyrinth seals prevent steam from leaking out of the casing along the rotating shaft. Next is the governor system. It helps to regulate the speed of the turbine by controlling the amount of steam entering the casing. Next is the overspeed trip system, a safety device that independently and automatically shuts down the turbine by closing the main steam valve if it exceeds a safe speed. Lastly, turning gear, a system used to slowly rotate the turbine shaft when it is not running to ensure even cooling and prevent bending. The propulsive characteristics of a steam power plant describe how effectively the plant converts the thermal energy stored in steam into useful mechanical power that produces thrust or propulsion. The steam turbine is the central component that transforms heat energy from steam into mechanical energy. This mechanical energy can either drive a generator to produce electricity or drive a propeller to produce propulsion. The steam turbine demonstrates one of the most efficient ways to convert energy stored in steam into useful work. So this is our operating parameters. We have the boiler pressure. Its symbol is P1, unit MPa or megapascal, and its typical range is 8 to 16. So next parameter is the steam temperature. So we have the T1. Its symbol, unit is degrees Celsius, and its typical range is 450 to 550. Next is the condenser pressure. So the symbol of condenser pressure is P2. The unit is kilopascal. Typical range 5 to 15. Next is the steam flow rate. We have this symbol M with the dot on the top, right? And its unit is kilogram per second, and typical range 10 to 100. Next parameter is the turbine efficiency. we have this N subscript T. Then the unit is percent, and typical range 80 to 90. And lastly is the propeller efficiency. Symbol is N, then P. Then the unit is percent, and typical range 70 to 85. So a lot of you guys might wonder what is the purpose of typical range of each parameter. So it represents the standard or commonly encountered values under normal operating conditions for a given system, such as a steam power plant or marine propulsion system. These ranges are provided to ensure that designs, analysis, and simulations are based on realistic and practical values. Operating within the typical range helps maintain safe and efficient performance by preventing excessive mechanical stress, thermal damage, or efficiency losses in components like boilers, turbines, and condensers. Furthermore, these ranges serve as useful reference points for engineers when selecting equipment specifications, optimizing system performance, or comparing different designs. In essence, the typical range indicates the expected safe and efficient limits for system operations, ensuring that the theoretical calculations align with real-world performance. So if a plant's boiler pressure is 10 megapascal and the range is 8 to 16 megapascal, it means the plant is operating within normal and efficient limits. If it goes below 8 megapascal, efficiency drops, and if it exceeds 16 megapascal, safety and material stress become concerns. So again, this is our operating parameters. So first is the boiler pressure. So its description is steam pressure at turbine inlet. So its effect on propulsion is higher pressure, more energy per kilogram of steam. Next is the steam temperature. Its description is superheated steam temperature. Effect on propulsion: higher temperature, greater turbine efficiency. Next is condenser pressure. Its description is steam exit pressure. The effect on its propulsion is lower pressure, more net work output. Next is the parameter, steam flow rate. Description: mass of steam per second. And its effect on propulsion: higher flow, higher power output. And lastly, turbine and propeller efficiency. Its description is conversion effectiveness: higher efficiency, better propulsion. So first is the boiler pressure. The boiler pressure refers to the pressure of the steam generated in the boiler before it enters the turbine. When the boiler pressure increases, the steam carries more energy per kilogram, meaning more work can be done by the turbine. As a result, higher boiler pressure generally increases both power output and efficiency. Second is the steam temperature. The steam temperature, specifically the superheated temperature, also plays an important role. When the steam entering the turbine is superheated to a higher temperature, it expands more efficiently and produces more work. So this leads to better turbine performance and reduced condensation losses, which improves the overall propulsive efficiency. Third is the condenser pressure. So the condenser pressure is the pressure at the turbine exhaust, where the steam is condensed back into water. If we lower the condenser pressure, we can extract more work from the steam because it expands over a larger pressure range. Therefore, a lower condenser pressure increases the net work output of the cycle, but it also requires more cooling capacity. Fourth is the steam flow rate. So the steam flow rate is the amount of steam passing through the turbine per second. A higher flow rate means more energy is available to produce shaft power, which leads to greater thrust and propulsive power. However, increasing the fuel rate also means higher fuel consumption and greater thermal loading on the system. Lastly is the turbine and propeller efficiency. So the turbine propeller efficiency determines how effectively the system converts thermal energy into useful thrust. A highly efficient turbine delivers more mechanical power from the steam or the same steam energy. An inefficient propeller converts more of the mechanical power into forward motion. Improving these efficiencies significantly enhances the overall propulsion performance.
Hello everyone, once again welcome to my channel. This is Kurt, and you are watching Kurt M3H. And for today's video we're talking about the steam turbine principle, and its general types. But before that, let's go take a look on what is a steam turbine in marine application. Marine steam turbine is a mechanical equipment found inside the engine room. It is used to drive the auxiliary machineries like pumps and generators, rotors, or even the main propulsion system of the ship. But how do the marine steam turbine works as a prime mover and a driver to the rotating machineries on board ships? To create a rotating motion of the turbine shaft, the steam turbine needed an external force to do a mechanical work. As the name suggests, the turbine uses the energy of the steam produced by the boiler, by extracting the thermal energy from pressurized steam and convert into a mechanical rotating motion. The rotating motion output of the steam turbine is used to drive the auxiliary machineries. The turbine is connected to the pump directly by coupling, and for alternator and propulsion system, the turbine is connected to a reduction gear to reduce the speed from 1000 rpm to 100 or less. Let's proceed to the two general types of the steam turbine, the impulse and the reaction turbines. In the impulse steam turbine, the rotor spins due to the force, or direct push of the steam on the rotor blade's bucket. As the illustration shows, the steam is directly pushing the rotor bucket by the use of the steam nozzle, while the reaction steam turbine spin and works from the reaction force, when the action force of the steam passes through the rotor blade curves. Here's a quick highlight distinction between impulse and reaction turbine. The blades of the impulse rotor are symmetrical in form due to their shape and size similarities, while the reaction blades are asymmetrical in forms due to blade sizes and design differ in every stages. The speed of the steam in impulse turbine is higher, while the reaction turbine the steam speed is lower. Also, the impulse steam turbines are having a high blade potency curve, while the reaction turbine blade potency are lower. And that is all for the steam turbine principle and basic types of construction. On the next video, I will be discussing the steam turbine construction, mounting, parts and safety system. If you like this video, please don't hesitate to hit the like button, and if you have a video request regarding marine engineering, please drop it down in the comment section. It will be my pleasure. Thank you for watching and see you on the next one.
Steam power plant for ship propulsion. Basically it consists of water tube boiler, steam turbine, condenser, boiler feed pump, gearbox, and propeller. Steam is generated in boiler from water and superheated. Superheated steam passes through steam turbine and thermal energy in steam is converted to rotational mechanical energy in steam turbine. High rotational speed is reduced to lower speed in gearbox to turn the propeller. Exhaust steam in turbine is condensed in steam condenser to water. Water is pumped back to water tube boiler by boiler feed pump.
Ever wondered how a steam turbine works? Let's break it down in 60 seconds. First, water is heated to produce high-pressure steam. This steam enters the turbine and hits the blades at high speed. The force of the steam makes the blades spin, converting thermal energy into mechanical energy. The spinning turbine is connected to a generator. As the turbine spins, it drives the generator, producing electricity. Steam turbines are used in power plants to generate most of the world's electricity. So, the next time you switch on a light, remember the power of steam turbines. Thanks for watching. Don't forget to like, share, and subscribe for more quick science shows.
Alright, that concludes our week 14 presentation on the propulsive characteristics of a steam power plant. I hope you now understand how turbine components and operating parameters influence propulsion performance. Thank you for listening.